Okay, welcome to Applied Mathematics at Northeastern State University. This is our video number 8. This is our last video for the whole semester. And supposedly when you're watching this video is the 8th week of this class, the last week. And hopefully you enjoy this class and the video. Again, the online class is normally difficult to do because we lose the interactions between human beings, right? But hopefully you learn something from it, and hopefully enjoy those videos. Okay, now in this video we will talk about the last chapter in our plan, which is actually chapter 1 in the book. Is actually part of the part 3, including geometry and logic. Okay, again, the reason we put this chapter to the end of the class is because it is a little bit abstract. Okay, from the content point of view. Okay, we certainly do need logic and do need to think in terms of the thinking ability in terms of doing mathematics, but most time we just do it based on our intuition and common sense. We don't even need to know a thing about logic to be able to think, right? But certainly to understand certain basics about logic can help us to think better, think deeper, and think correctly, right? Avoid mistakes. So it is useful to talk about this chapter anyway. So that's why I put it toward the end of this course. Now, again, let's start from a joke in mathematics. Okay, unfortunately, I didn't find any jokes in logic. And I do find some ones about good ones about statistics. So let's just do another one about statistics. Okay, here it goes. There was a statistician, which is basically somebody working in the statistics, right? There was a statistician drowned crossing a river. The average depth of water in the river is 3 feet. Does that make sense to you guys? Okay, let's start chapter 1. Okay, I'm gonna use an order that's a little bit different from the book. I don't really like the order of the book. It makes things more complicated than it should, and I will also only talk about the key points in this chapter that you need to know. So not everything in this book in this chapter is equal. I think this chapter is written pretty well, but it's just written in a way that looks more complicated than it really is. Okay, let's start from sharing the screen. Okay, what do we need to know about logic? Okay, again, the title of this book is Thinking Critically, right? But essentially that means what it's talking about is here is in order to think critically, you have to understand logic a little better. Okay, so now why do we need logic? Okay, basically whatever you want to do, right, in terms of thinking, right? Essentially what you're doing is making some statements, right? Some arguments, right? All of these have to follow logic, right? And not only about that, right? You want to do some calculation, right? You have let's say you have a project, you want to do this and this and this to get the project done, right? Now, again, you have to, these things you do has to be logically, can lead to you logically to the results or the product that you want to get, right? Now, certainly for all of this, okay, we need logic. Okay? Logic is just something that we cannot live without. Okay, now we use it all the time, although we don't we're not aware of it, and a lot of time we don't really need to know it consciously because kind of like built in, like kind of what we call common sense, right? But it is useful to go through it and then make it clear, and then maybe you pick up some holes that you didn't realize before in the argument you made, or when you listen to somebody else's argument. So this whole chapter will definitely help you in terms of improving your thinking ability and improving your approach to whatever task you're given. Okay, so let's start from something really basic. Okay, let's first talk about proposition and logic connectors. So what is a proposition? Okay, it is basically kind of like a statement. So whenever you want to make an argument or whenever you want to think something, right? Essentially, what comes to your mind or what comes out of your mouth is a bunch of statement. Okay, say I'm happy today, right? Or I wear a green T-shirt today, right? These are all statements. Okay, those statements. What we care about logic-wise is whether it is true or false, right? It can be either true or false. Okay, so these are called all of these kind of statements called proposition, okay, in logic. Okay? So, but again, there's two possible state of the statement, okay, or a proposition. Okay, it can be either true or false. Certainly, it cannot be both true and false, right? It can be either true or false. Okay. Now, what about logic connectors? Okay, these are just something we use in our proposition or our argument, or this is basic logic relation you can have. Okay, let's say suppose you have one proposition we call P, and then another proposition we call Q. Okay, let's talk about a couple of logic connectors. We can connect these two propositions by a connector called AND, P and Q. Okay, so what is the result of this connector? Okay, let's say if P is true and Q is true, then certainly the AND position, when you connect them like AND, P and Q certainly is also true. However, as far as one of them is false, either P or Q is false, then the result of AND is going to be false. Okay, and then if both of them are false, then the result is false. Does that make sense? So only if both P and Q are true, then P and Q is true. Let me give you an example of the AND condition. Okay, let's say I want to go back to China in the summer, okay, or anytime. Okay, for that there's two conditions I have to, it has to be satisfied. I have to have money and time. Right? Certainly, as we understand, right, both of them are necessary, right? We don't have the money, certainly I cannot buy tickets, I cannot go. If I don't have time, even if I have money, I cannot go, right? So either one of them is necessary. So this is exactly the P and Q situation we have. So only if both these two conditions are satisfied, then I can go to China, okay? And if only one of them is false, I cannot. So that actually give you a good example of P and Q. Okay, now a second logic connector we have common is P or Q. Okay. Now again, I think all of these essentially is your common sense or your intuition. Okay. In this case, right, certainly if P and Q are both true, then P or Q certainly is true. Okay. And if only one of them is true, then your result is true. And it only false if both of them are false. So in this sense, it's kind of easier to meet. Let's talk about the example of the OR connector case. Okay, let's say in this case, let's talk about the condition for my happiness. Okay, I could say that either if I'm working or if I play with my kids, make me happy. Okay, so in this case, either this condition or the second condition is satisfied, then I'm happy. I don't need to both work and play with kids to be happy. Okay, I could be happy either by doing work or playing this kid. Okay, this seems like a pretty ideal situation for life, right? And so that tells you happiness is not that difficult to get, right? Anyway, this serves as a example of this or connector. Okay, now another one is called not connector. This actually works only for one proposition. Like if you put one proposition here, not P means if P is true, if P is true here, then not P is false. And if P is false here, not P is true, right? That's pretty simple, right? So if I'm saying that I'm wearing a t-shirt, that if that is true, then I'm not wearing a t-shirt must be false, right? That makes sense? Okay, and then finally we have this connector, if, then, okay? So this two keywords connects two propositions together, and this is kind of like the condition, right? This is the kind of like the result of it, right? And you could form a lot of this kind of a condition, okay? For example, if P is right, then Q is right. If P, then it's Q, okay? Or if not P, then not Q. If, and or you can form like if Q, then P. And finally, you can form something like if not Q, and then not P. These four statements, I mean, the four propositions are all, they are related. Okay, this one is, I mean, it's called normally conditional proposition, right? And then this one, really, that the first one is called inverse. So you inverse each one part of it, right? Not P, then not Q. Now this one, really, the first one is called converse. Okay, so you kind of reverse the order. Okay, you put this conclusion here and then the assumption here. Okay, the last one is called contra positive. Now, interestingly, it turns out logic-wise, okay, the first one and the last one are equivalent, while the second one and third one are equivalent. Let me give you an example. Okay, let me use this statement here, okay, as the conditional statement. Okay, if I take a course, then I study for it. Okay, this seems like very, very reasonable thing, right, to say, right? If I take a course, then I study for it, right? I think is almost like universally true, right? That makes sense, right? Now, based on this discussion, right, the contrapositive statement or contrapositive proposition should be correct as well. Okay, what is the positive one? Okay, that means if I do not study for it, then I do not take the course. Does that make sense? And logically, these two statements are equivalent. Okay, if I take a course and I study for it, is completely equivalent to say that if I do not take study for the course, I do not take it. Okay, and then let's look at the second one and third one as well. Okay, what is the inverse statement? Okay, the inverse statement is if I do not take a course, then I do not study for it. Okay, certainly this one is not equivalent to the original statement. Okay, because certainly if I do not take a course, I may still study for it, right? Maybe just for fun or something, right? Now the third statement, right, in this case would be if I study for it, then I take a course. Again, that may not be true, right? Maybe I studied for, again, I can study for fun. That doesn't necessarily mean that I do not study for. But if you look at it, right, these two themselves are equivalent logically, right? Again, this one would be if I do not take a course, I do not study for it, it is completely equivalent to say that if I study for it, then I take a course. Again, these two are equivalent. Both of them may not, doesn't feel like good, but they're equivalently, they're saying the same thing. Okay, so this is the if then a connector. Okay, now overall, right, all these logic connectors are kind of like mathematic operations like addition, subtraction, multiplication, division. Okay, but they're used for connecting propositions or statements. Okay, that makes sense. Okay, the second topic we want to talk about is called sets and Venn diagram. Okay. Okay, what is sets? Okay, actually, it turns out sets is actually very, very fundamental mathematical object. It can be used to talk about anything, but for this for this class, we don't have to know a whole lot of it. It's just like we should just understand it very simply, right? A set is basically a set of things or set of objects, whatever object you're interested in, right? Let's say if you're interested in mathematics, you can put those objects. You can talk about objects like arithmetic, algebra, and algebra and geometry, right? This will be like one of your sets, okay? Or if you like sports, right? You can talk about like basketball, baseball, soccer, etc., etc. Okay, so all these objects form a set. Okay, now why do we need to talk about that? Okay, it turns out that in a lot of argument or discussion, people mention things, right? When they mention them, essentially it's kind of like a set of things they mention, and it's helpful if you understand this concept of set, and especially if it's helpful if you understand which object belongs to which set. Okay, now certainly within one set you can talk about some subsets. Okay, like it's a set of a set itself. Okay, now one way to represent those sets is a Venn diagram. Okay, so let's talk about the Venn diagram. This way you understand what I'm talking about when I say a set and subset. So what is a Venn diagram? Okay, it's actually a very simple idea. It's just a way to picturize a set. Okay, let's say you have a set. I call it like mammals. Okay, it contains objects, all kinds of mammals you have, right? Now you can certainly have a subset of this original set, right? For example, I can talk about like tiger. It definitely is a mammal. Or you can talk about a whale. That's another subset. Or you can talk about human, right? We are also mammals. So you can have a subset of a set. Okay. Now certainly you can go further than that. You can go smaller, even smaller subset. You can categorize all tigers you have, or categorize all whales, or all humans, right? You can go in an infinite number of levels. It depends on the question you're interested in and everything. Okay. Now one interesting thing is sometimes there's those subsets could overlap. Okay, it depends on how you categorize your thing. Certainly, in this simple example, there's no overlapping between tiger and human, or human whale and tiger, right? It's just not possible unless in a sci-fi movie or something, right? Those are just belongs to different things. Okay, but if you in some other cases they may overlap. Okay, it depends on how do you categorize. Okay, let's say in one case, right? Let's say if you talk about let's just say a set of people in US. Okay, now you could have a subset of teachers. Okay, that actually is everybody that has a job. It depends on how you define, right? Everybody has a job as a teacher, right? You could have another subset as man or male, right? And certainly these two subsets definitely overlap, right? Now, what is the overlapping part? Okay, it's basically this part here is means that all the object in this part belongs both to the set of teachers and to the set of men. So we're talking about male teachers like me, right? I'm a teacher, right? So I'm in this part. Okay. Now, what about this part? This part here, because it's not overlapping with teachers, that means we're talking about men that do not have a job as a teacher. Well, what about this part? This part means that because it does not overlap with the category of men, that means we're talking about teachers. They are not men, okay? So mostly we're talking about women here, right? So again, to draw these Venn diagrams like this, it helps you to understand, okay, logically, okay, which object belongs to which set and or belongs to which subset. So next time when you listen to somebody giving you an argument, right, there's a lot of things, a lot of categories they talk about. It helps if you draw a Venn diagram and clearly understand for yourself which part of the diagram they're talking about, et cetera, okay? Because sometimes they could easily cheat you by talking about something that's not belongs to the appropriate set or something, okay? Does that make sense? Okay, as another example, let's look at this three sets. A set of color red and green and blue, okay? Now, when they overlap, that means this area, it has both red and green, and then you have a color of purple. So purple is nothing but red and blue. Red plus blue give you purple. Well, red plus green gives you yellow. Well, green plus blue give you light blue. Now, interesting, when you combine all the three colors together, this is the spot that all the three colors are represented, and then you got actually white, right? This is again another interesting good example about the set and then the overlapping the sets we talked about. Okay. Okay, the last part I want to talk about is number 3, arguments. Okay. So what is an argument? Okay, an argument in some sense can be broken down to 2 parts. Okay, there's a premise part, and then there's a conclusion part. And normally you may have one premise, or normally have 2 premises normally, okay, or 3 or 4 or multi premises, okay, and then you make a conclusion out of these premises. Okay, now there's 2 kinds of argument in general. Okay, the first kind is called inductive arguments. Okay, and the second kind is called deductive. Okay, let me give you an example. Okay, in both cases. Okay, now let's start from inductive argument. Okay, let's say, okay, the premise 1. Let's say, if you threw a ball, it goes back to the ground, right? Threw a ball, it falls back to ground. Now, this is premise 1. Okay. Now premise 2. If you threw a book, you threw a ball into the air, it falls back, okay, to ground. Now you can make a few premises, like you can throw another object into the air and it falls back to ground. Okay. Now after a bunch of these premises, you can make a conclusion that whatever, for all the objects you threw into the air, it falls back. Okay. All objects threw into the air. I'm just writing it concisely because we don't have to be that. You understand what I'm saying, right? Now this argument is actually an inductive argument. Okay, why is it inductive? Okay, because the set of the object appeared in this premises, okay, it is smaller than the set in the conclusion. Okay, so we're actually in this sense we're actually predicting something. Okay, we're making a hypothesis. Okay, we're generalizing what we know, the fact we know. Okay, so certainly the ball, whatever object you use here, right, is a specific object. It's certainly you cannot actually do an experiment and run all kinds of objects that are available. I mean, it'd be really time consuming. You have to pick up any single one of them. But based on these observations or the premises you make, you can make a conclusion that it seems like all objects should, I mean, if you throw them into the air, it should fall back. Okay. Now this conclusion may or may not be right. Okay, because you're doing an induction, and so you start from your premise in a set, and then you want to generalize it to a bigger, to your conclusion in the bigger set. Okay, so it may or may not be right, but it is useful a lot of times. Actually, if you look at science and mathematics, the way we making progress is by doing those induction kind of a deal. Okay, by making predictions and hypotheses and check. I mean, then later we can check our hypothesis or induction. I mean, prediction. But if you don't do induction, you cannot get anything new. Okay, that makes sense. Now, as we know, right, this conclusion here is actually not correct because, as some of you know, right, for a rocket or a space shuttle, right, you threw them into the air, they could go out of space, never fall back to the ground. Okay? So it may not be right. Now you have to specify some other premises, like the speed of something is not higher than 7.8 meter per second or something. Then, sorry, 7.8 kilometer per second. Then this conclusion is right. So you can add more premises to it, but it's still useful to make inductions. Okay. So for these kind of argument, you cannot say it is wrong or right because again, we're predicting something. We're making something new out of it, the old things, right? We're generalizing things. So the only thing you can say, you can feel about is either it's a strong argument or is a weak argument. Okay. So you have to judge it kind of like a subjectively. Okay. Now, what about deductive argument? Okay. This kind of argument is actually the opposite. Okay. So using the same example, we would do it like this. Okay. We would make a premise. Okay. All objects through in the air fall back. Okay. If we take this as our premise, then we would conclude that the conclusion would be if you threw a ball to the air, because the ball is a object, so it should fall back. Now, again, the nature of deductive argument is exactly opposite to the inductive argument, right? In the case of inductive argument, you start from a set that is big, and then you go to when you're in the conclusion, you make a conclusion in a subset of the previous set. Okay, so this seems like may seem like make all the deductive arguments safe, right? This should be right, right? But not necessary, right? There could be two things could be wrong with your deductive argument. Firstly, your premise could be wrong, right? See, in this specific case, right, all objects through in the air falls back, as we know, is not correct, right? Like rocket and space shuttle. So when your premise is wrong, even if the argument itself is valid, then the argument may still be wrong, right? Now, secondly, it could be that the premise is right, but the argument itself is wrong. It's not valid. Maybe you have this premise given in a set. Well, you are actually talking about in the conclusion a set that is not exactly a subset of this previous premise, right? In that case, it could be wrong, right? For example, you can say that, let me give you a false deductive argument, right? Let's say we can say that all objects that moving slower than a certain speed, if you throw them into air, it falls back. Let's say something, and then from that you conclude a rocket being thrown into the air has to fall back. That is not right. The reason is the rocket, when it's speeding, I mean, it's moving with a faster speed than the speed given. Does not belong to the set that talked about in the premise. In that case, the argument is again not right. Okay. Now, if the argument is right but the premise is wrong, it's still called a valid deduction. Okay. Well, when the premise is right, it's called sound deduction. Okay. Now, only you have both valid and sound deduction, then the deduction is right. Otherwise, it's wrong. Does that make sense? Hopefully, you understand what I'm talking about. Okay, the 3 points we talked about so far corresponding to unit 1B, 1C, and 1D. Okay. Now, after you understand those 3 points, you could actually go and do 1A and 1E easily. Okay. So 1A talk about all kinds of fallacies you can make in making an argument, and they give you all kinds of scenarios of fallacies that you can have, right? Like circular reasoning or wrong premise or whatever. Okay, go read them and then just get an idea. And this typical fallacies can help you to figure out whether an argument is wrong or right when you face some arguments, right? Now, 1E talk about thinking critically. Okay. Okay, now certainly the book gives you some good suggestions, okay, but let me give you my 2 cents on thinking critically, okay? How do you think critically, okay, or think correctly, okay? Now, one way you may think of is I should keep all we learn in this chapter in my mind, okay, about those logical connectors and proposition, and then about this Venn diagram and set, and then about the inductive and deductive arguments, etc., etc. I would say you don't have to do that. Okay, it's a lot of the details. Okay, it will not help you to think. Okay, how do you think? Okay, to think critically is a simply matter of using your common sense. Okay, and now, but it's a little more than the common sense. Okay, while you have your common sense, also keep a reasonable doubt. Whatever you think about, a argument by a politician or a discussion by an instructor like me, or whatever you want to think about, what you want to argue, right? Use your common sense and also keep a reasonable doubt. Okay, whenever you feel like there's something fishy there. Okay, maybe a little bit doubt about something. Maybe I feel like there's something wrong with this argument, or I feel like there's something wrong with what he's talking about. Okay, then go back to the discussion we have here. Use the tools we learned here, okay, to figure out maybe there's actually a problem here. Okay, now to do that, you again use the way to solve problem, the problem-solving approach I talked at the first video, right? Break down the problem into smaller problems, simplify the problem. Okay, break down the argument to pieces. Okay, to premises and conclusion, and then go through them one by one. Okay, check very carefully until you figure out where the problem is. A lot of times when you have a doubt about something, it turns out that it will be that the something is actually indeed false. Okay, well, occasionally you would have a doubt, but it turns out that everything's just fine. It could happen. Okay, and those will help you to build up a better common sense. Okay, a better intuition. Okay, learn from those cases. Okay, that can help you to purify your common sense to make it better, to make it work better for you. Okay, now after you repeat this process again and again for a few months or a few years, if you do it carefully for everything, eventually you build up a very well common sense, a very strong common sense that you can use, like a very strong intuition. So whenever you hear something, you immediately tell whether there's some fallacy there or it is a correct argument about something, or when it's wrong, what part is wrong. Okay, like in my case, for example, when I hear something, a lot of time, 99% of time, like an argument from a politician or from a commercial about advertisement of something, I could tell which part is wrong and why it's wrong, right? But it takes a lot of practice. But on the other hand, it is a very, very useful thing to have to know. I would say is one of the fundamental ability, a skill you should have for your life to be able to think critically. Okay? It will help you tremendously, both in mathematics and out mathematics. It just very, 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 it actually make you in some sense, make you complete as a human being. Because like what Descartes said, right? I think, therefore I am, okay? Based on what we learn from this chapter, this statement, I think, therefore I am, is equivalent to another statement. If I'm not a human being, then I cannot think, right? These two are complete equivalent statements, okay? So I could emphasize this like all day, all night, okay? But this is just very, very important if you can think critically, if you make you a different person, okay? If you make you a very strong and very powerful person, okay? If you can think critically, okay? Keep this in mind, okay? Okay, that is it for today. And thank you for watching this video and for watching all the videos of this course. Okay, for the question for bonus point, right? Based on your experience, a false argument you heard either from a advertisement or from a politician that you heard like it doesn't make sense, and explain why it does not make sense based on what you learned from this chapter. Either maybe the premise was wrong, or it may be doing a induction, a generalization which is not justified, or maybe the argument in the deduction part is wrong by itself, or is actually trying to tell you a statement is equivalent to the inverse statement, which is not, right? Try to list the reason for this, why this is false, okay? I think it's a really good exercise for you, and you can get the bonus point if you do that and send me email, okay? And again, thank you very much, and have a good summer and the best luck for your exams and the final.